Hello everyone. Welcome to this seminar. Today we have Carlos Melo, the first speaker of this semester. Carlos is a Brazilian PhD candidate in astrophysics here at Universidade Federal of Rio Grande do Sul, with the focus on using strong gravitational lensing and stellar dynamics to probe the mass distribution of galaxies. Last year, he completed a PhD internship at the Institute of Cosmology and Gravitation in Portsmouth, in the United Kingdom. And previously, he earned a master's in astrophysics here and a bachelor in physics from Universidade Federal de Juiz de Fora. So the floor is yours when you're ready.
Thank you for the introduction, Daisy, and thank you all for being here and seeing this seminar. Today, I'll be talking about this recent work that we just put on arXiv. So if you want to know more about this work and see the details, you can scan this QR code here and see the draft that's now on arXiv, but also submitted to the monthly notice. And yeah, so today I'll be talking about a 36 billion solar mass black hole at the heart of the Cosmic Horseshoe gravitational lens. And I want to start this talk breaking this very big title into pieces and try to address the parts of the title here. So beginning with gravitational lenses, this is a phenomena predicted by Jar that happens when we have galaxies behind galaxies, and the foreground galaxy, this one, close to the observer, which is our telescope, is so massive that the gravitational potential of this galaxy will curve the space-time around it, and the light rays coming from the source galaxy, which is this galaxy, the most distant one, once the light rays cross the neighboring of the lens galaxy, the light ray will follow this curved space-time, and we will be observing the source galaxy into multiple positions in the sky, and also in a distorted way, just like this figure right here. So this is how we are observing with our telescope this source galaxy right here. And this is because of the deformation of the space-time caused by the mass distribution of the foreground galaxy, also called lens galaxy. And the mathematical description is quite simple, to be honest, because this deflection that we are observing can be understood by the deflection angle, which is nothing more than the difference between the original source position on the source plane, in this figure right there, and the observed position that we are seeing after the being lensed, which is the position right here. And so just to talk about a bit about the equations involved right here, this is called this one. It's called the lens equation, which is relating the original source position with the observed one through the deflection angle, which is this alpha right here. But the important thing that I want you to keep in mind from this slide is the equation for the deflection angle, which is this equation right here. And the important thing about this equation is this kappa quantity, which is the surface density profile. Actually, this is called convergency, but the convergency is just the surface mass density normalized by some constant. So the important thing to keep in mind for the rest of the talk is that the deflection angle depends basically on the mass distribution of the lens galaxy and the positions that we are observing the deflected source. So moving on, someone could ask, why do we care about lenses? I would say that because this is a very rare phenomena and very interesting as well. We have this distorted galaxies, but we can also do a lot of science with gravitational lenses. If you are aware of the Hubble constant and the Hubble tension, which is the tension between different measurements of the expansion rate of the universe, we can actually use gravitational lensing if the source is a variable source, to measure the Hubble constant, the 8 naught. We can also use gravitational lenses to probe dark matter substructure within galaxies, because the way we observe the deflected source will change if you have some substructure in the lens plane. Because of the magnification effect, I'll not be talking about the magnification, but gravitational lenses, they magnify the surface light profile of the source. And because of that, we can observe very right redshift sources due to the gravitational lensing phenomena. So by doing the modeling, we can actually reconstruct the source and study right redshift galaxies. And there's a lot of things that we can do, including constraining or detecting supermassive black holes, which is one of the topics of this presentation. To the next part, the Cosmic Horseshoe is one of these gravitational lens systems, but it is a very special one because the Cosmic Horseshoe is one of the most massive galaxies ever observed, and probably the most massive lens galaxy observed nowadays. The mass of the galaxy is this red spot right here, is almost the mass of a cluster, so something around 10 to the 12 star masses. This is huge. And the foreground galaxy is lensing a star-forming galaxy at a much higher redshift in this almost full Western ring in blue, just right here. So it's a very well-known galaxy. But this galaxy is even more special because so far I was talking about just one lens and one source galaxy, so we have just one deflection. But this system is actually a compound lens system, which means that we have another source in the same line of sight. So instead of having just one lens and one source, we have one lens and two sources, meaning that the light coming from the most distant source is actually being lensed by the source one and being lensed again by the main galaxy. And this kind of configuration is what we call compound lens system. And this is very special because when you observe the galaxy, just like here, we have information in two different radii. We have one information coming from this ring arc right here, which is a galaxy at redshift 2.4. And we have another information coming from the intermediate source, which is source 1 right here at redshift 2, that's being lensed in this radial arc right here. There's a zooming of the radial arc and a counter image just right there. And this is important because in this way, we can constrain the mass distribution. If you remember, this is an important quantity for gravitational lensing. We can constrain the mass distribution in two different radii, not just within the ring, but actually in the ring and also in the inner part of the profile or the potential, where we believe the black hole will be. So this is very good to constrain the black hole mass, because this radial arc will be sensible to the presence of a black hole near the center of the galaxy. Yeah, so talking about black holes, actually, I just want to talk about a class of black holes, which we call supermassive black holes, which are these huge black holes in the center of the galaxies that we've been observing in nearby galaxies quite long right now. And we have like these observations right here. When this black hole is creating materia, they became a kind of AGN, active galactic nuclei, and they will release like this jets, and so on and so forth. But again, we can ask ourselves, why do we care about black holes? Someone could say because they're nice, but there's also important correlations between the black hole mass and the structures and properties of the host galaxy. And some of these correlations are between the black hole mass and the galaxy bulge luminosity. between the black hole and the stellar bulge mass of the galaxy. But for this talk, I'll be focusing on one particular relation, which is between the black hole mass and the stellar velocity dispersion within the effective radii of the galaxy. So in this plot, we are seeing the black hole mass as a function of the velocity dispersion, the sin-log scale. And this is the main relation right here. And there are different methods for measuring the black hole mass. And actually, here we have different morphological types and different types of galaxies. And what this picture here are telling us, and all this scaling relation as well, is that we have some kind of connections between how the galaxy evolved and how the supermassive black hole evolved within the galaxy. So this is pointing that for a co-evolution between the host and the black hole. And this is important because in a galaxy formation scenario, we want to understand how galaxies evolve through cosmic time, and black hole seems to be very important for the evolution of the galaxy. And just to mention another important thing about black holes, as I said, when they are creating material, they become a AGN, and this AGN will release energy to the surroundings in the inner part of the galaxy. And this energy has a lot of implications because they can trigger star formation, but they also can quench star formation, and this will alter how the galaxy evolve. The AGN can also be used to try to understand the CRISPR-4 problem, which, well, it's a problem between, not between, but it's a problem around the central mass distribution of halos. And yeah, so there's a lot of connections between the black hole and the host. But yeah, one question that's important for this talk is how can we spot or how can we find these black holes? Especially when this black hole is dormant, which means that they're not accreting any material. And by definition, a black hole is not visible by light. So we need to find alternative ways to detect the black hole. Yeah.
कुछ तो है सुपरमैसिव ब्लैक होल में कुछ तो अंग्रेज
Can
पढ़ा
someone mute Jay? Jay, can you mute yourself?
प्रोजेक्ट वाला बहुत लगा
Carlos, muta o...
Sim, estão mutando.
Tá. Obrigada.
So yeah, so in this talk, I'll be briefly introduce two ways to find black holes, or two ways to detect the influence of the black hole. And one, of course, is through gravitational lensing. As I said, gravitational lensing is sensible to the mass distribution. In these simulations right here, we have two simulations of a gravitational lens. On the right here, is a simulation without the black hole, and on the left, we have a simulation with the black hole. 10 to the 10 solar mass black hole in the center of the galaxy. And as you can see, this is a zoom in on the radial arc, just right here in the center of the galaxy. Because of the presence of the black hole, this radial arc changed its shape and also changed the flux. And we're not seeing anymore this extra flux right here. And this is the effect of the gravitational potential of the black hole near the center of the galaxy. So observing radial arcs and comparing the observations with our models, we are able to constrain how massive a black hole can be in order to reproduce the observations. So this is a way to detect supermassive black holes when they are not accreting any material. And a second way is through the kinematics of the stars and sometimes the gas around the black hole. Because again, the kinematics I will be talking later is mainly described by the gravitational potential. And once you are close enough to the black hole, the stars and the gas near the black hole will feel the potential of the black hole, and this will change the motion of the stars. In this case, I'm talking about stars, but can also be gas. So again, this is a simulation of the velocity field. This is the velocity dispersion map for a simulated galaxy. On the right, we don't have a black hole. And on the left, we have a 10 to the 10 solar mass black hole. And by this map, we can see that the velocity dispersion increases a lot from this panel to this panel. But you can also see this on the radial profile. This is the velocity dispersion radial profile. And if you look close, here we go from 200 kilometers per second to 300 kilometers per second. And this is only because we have a black hole near the center of the galaxy. So it's another way to spot a black hole using a tracer when the black hole is not accreting any material. And talking about stellar dynamics, I just want to briefly introduce what is stellar dynamics and why do we care about this at all. So stellar dynamics is a branch of astrophysics where we aim to describe the dynamical and kinematics state of the system. And we can do a lot of things knowing this information. Unfortunately, the mathematical description in this case is not very straightforward, as in the lens case, because here we need to use a lot of statistical physics and some assumptions in order to describe the stellar motion and the phase space distribution of the system. But again, one thing that I want to highlight and I want you to keep in mind for the rest of the talk is these two equations right here. These two equations describes the stellar velocity dispersion given a gravitational potential. And the important thing here is this phi, which is the gravitational potential. And once you have it, in principle, you can solve these equations and describe the whole dynamical state of the galaxy. And as we know, the gravitational potential is described by the mass distribution. And again, the important quantity here is the mass distribution of the galaxy. And again, if you know the mass distribution, we can do a lot of things using stellar dynamics, like probing the inner mass distribution of the galaxy. Different populations of stars will have different, will occupy different positions in the phase space. So you can use this to break the galaxy and identify different structures and different stellar populations as well. This is what I'm showing in this plot right here. Here we have some observations. This is the velocity field, velocity and velocity dispersion. And here we have some stellar properties like age and metallicity based on a stellar dynamical modeling. And of course, we can also use, as I showed in the previous slide, the stellar dynamics modeling to spot black holes. So nice. Now I think we have everything to proceed with the rest of the talk. And let me show you some of the data that we will be using in this work. So for the gravitational lensing part of the analysis, we have two images from the Hubble Space Telescope. They are high resolution images in two different filters. This filter F75 is in the blue part of the spectra. So this filter is better to see the gravitational arc, because as I said in the beginning, the sources are star-forming galaxies, and they are better traced by a blue filter in this case. So in the plots, we are seeing the observed data. This is the residual after we remove the lens light here. And this is a zooming. The resolution is not so good, but the zooming in this central region of the galaxy. And you can see just right here, the radial arc is very fainty, but it's there. And this is what we'll be using to constrain the inner mass distribution and also the black hole mass. And we also have a more red band, or more redder image in the filter 814, which we'll be using to trace the stellar mass distribution, because the red bands are better in tracing old stellar populations, and this is where the bulk of the stellar mass are concentrated. And for the stellar dynamical analysis, we'll be using a MUSE data cube. For those that are not familiar with a data cube, data cube is basically it's a cube, as I said, and in each image in its slice in 2D, we have an image of the galaxy in some wavelength. And if you extract, and in the third dimension, we can extract a spectra in each position of the galaxy. So basically, this is an image of the cube. This is showing the signal to noise. And in each pixel here in this image, we can extract a spectrum, just like that, this one. And by modeling the spectra, we can measure the velocity and velocity dispersion related to that spectra. And by doing that, we can construct this stellar velocity dispersion map right here that will be used for the dynamical part of the analysis. Again, the resolution is not so good, but anyway. And this plot here is just the radial profile of this map right here. So it's a velocity dispersion radial profile. So yeah, a few things that we can do with this data set, and a few things that I'll be talking to the rest of the talk, is related to the inner mass distribution of the main lens galaxy. So the main deflector right here. And it's important because we can map in two different radii, as I said, the stellar mass, the dark matter mass, and the interplay between these two components. We can use this information to give some hints about galaxy formation models. And of course, because it's on the title of this talk, we will be also using this information to constrain the black hole mass in the center of the galaxy. And hopefully, to the end of the talk, I also want to give some insights about the diverse evolution pathways between the host galaxy and the black hole. Yeah, so just a bit about the methods, just to remember everyone. This is supposed to be a gift, but anyway. So yeah, for the lens modeling, we'll be using PiezoLens, which is a public software designed for lens modeling. And we'll be using a semi-linear inversion method. These are just names to keep in mind if you want to look for this later. But the idea behind this is that once you have the observed image, just right here, this image of the arcs, we need to propose some mass model. It's part of the modeling process. And in your mass model, we can put some stellar mass, some dark matter halo, a black hole, or anything that you want to put there to describe the mass distribution of the deflector. And by doing some linear algebra, we can invert the lens equation and reconstruct the source on the source plane. So this is the how the source looks before being lensed, and this is the result after the deflection caused by this mass distribution. But as I said in the beginning, the important feature to constrain the black hole mass is the radial arc, just right here, because this is the feature that will be sensible to the black hole mass. And the system is a compound lens system, which is pretty hard to model. So instead of reconstruct both sources in two different redshifts, we'll be using a compound approximation, which means that we will be only fully reconstructing the radial arc. So this image in red right here. And for the ring arc, this one, we will be only ensuring or forcing the model to reproduce the total mass within this arc. Yeah. And for the dynamical modeling, we'll be using a code called GEM, which solve these equations right here. I forgot to mention, this is just an example of how GEM works. This is like the data, and below the data we have the model. So just a few examples showing that gem is pretty good in reproducing the velocity field and the velocity dispersion field. Sorry, it's velocity right here and velocity dispersion on top. But what the gem does is solving these equations right here, given that you provide some mass distribution. And again, this is part of the modeling. And to ensure that we'll be using the same mass distribution to reproduce the lens part of the analysis and the dynamical part of the analysis, we built a framework that we are calling DyLens, which is a combination between the pi lens for the lensing, gem for dynamical modeling, and Dynasty, which is an asset sampling. And within this framework, we I forgot the word, sorry. We are assuming that the same mass profile will reproduce both data sets. And such that our model likelihood is actually a combination between the lens likelihood and the dynamical likelihood. So yeah, finally to the results. So for our fiducial model, we are assuming a very, probably the most simple model possible, separating dark matter from stellar matter. So in the fiducial model, we have one quantity related to the mass-light ratio, which is a way to convert between the stellar light that we observe with the telescope and the stellar mass that we are interested. We have one dark matter halo represented by an elliptical NFW profile, elliptical Navarro-Frank-White profile. And of course, we have the central massive black hole. So this is a very simple model, but as you can see here in the results, they are very good in reproducing our data sets. So this in the top left, we have the lens model right here and the normalized residuals. This seems pretty okay. And this bottom panel here are showing the reconstructed source on the redshift 2. The source is not very smooth, but could be probably a irregular source. This is completely possible. And right here, we are seeing the, in black are the observations for the stellar velocity field. And this magenta line, that's not visible, is our model. But the interesting thing to talk about this is how massive is the black hole. So this is the posterior distribution for the black hole mass, just in the center of the galaxy. And to be able to reproduce both data sets simultaneously, our posterior distribution, we have a mean of the posterior distribution of a 10 to the 10.56, solar mass black hole, which is a very massive black hole. But we could ask ourselves, how does black hole mass change if we change our assumptions about the mass distribution? Because I said, this fiducial model is quite simple, but what if we change some assumptions related to it? So here we have a lot of tests around the fiducial model. And in each of these models right here, we change one of the assumptions we made in the fiducial model at once. So for instance, like right here, the top left one, we replace the elliptical NFW profile to an elliptical GNFW profile. So there are more freedom in the slope of the density profile. And each of these plots, again, show the posterior distribution related to that model. And again, making this assumption right here, we recover a black hole mass with a mass similar or consistent with the mass we infer with the fiducial one. And we have variations of this. So instead of having one scalar mass-light ratio, we have a variable mass-light ratio. And again, the black hole mass is consistent or within 1 sigma credible interval if you compare this result with the result of the fiducial one. And the important thing to keep on this tests is that despite the variation we made in the fiducial model, our measurement is very robust and the black hole mass is still very high. But we can go further and try to change not just one thing on the master file, but change a lot of things simultaneously, allowing for a lot of freedom in the mass distribution in our mass model. So here we have a few alternative models where we change a lot of the assumptions about the model. I will not be talking about all of them, but for instance, we have these models right here, the three, where we set a GNFW model, a variable mass light ratio. We let the scale radii to follow a mass concentration relation. So in some sense, the scale radii is not a free parameter, but it's free to vary across samples. And we also have the black hole thing. And again, the black hole mass is still very high, despite the lot of freedom we have in this model. Which again points that our fiducial model, despite being very simple, changes of this model still reproducing a very, very high black hole thing. And this gives us confidence that the black hole we are measuring, the mass of the black hole we are measuring, is something statistical significant. But we can go, oh no, sorry, before we go beyond, we can also think about a model without the black hole to see if this black hole is really necessary or not. Because in principle, we can just do not put any black hole in the model and see what we get. So here, it's a model, the fiducial model. So same mass configuration. The only difference is that we don't have the black hole mass explicitly included in the model. Again, this is the lens model and the residuals, and this is the reconstructed source. By eye, we cannot see any differences in the lens model, but if you look at the dynamical model, we can see that we are not able to reproduce this central region of the velocity dispersion profile, which is the region more sensible to the black hole mass. Which means that to be able to reproduce both data sets simultaneously with some kind of confidence, we need to include some central point mass, and not just a point mass, but a very massive one. But we can go beyond qualitative comparisons to a more quantitative comparison, using what we call Bayesian evidence, a bias factor. So don't want to talk a lot about this, but the Bayesian evidence and Bayesian factor, it's a statistical way to quantify how much a model is supported by the data over another model. So by doing that, we can compare different models subject to the same data set and see which one is more likely in the statistical sense. So in this table right here, we have just a usual rule used for this. This is the Bayesian factor between two models. And a Bayesian factor greater than 1 means that the model with the highest evidence, highest Bayesian evidence, is significantly more supported by the data than the other model. And if you have a Bayes factor over than 5, this is a decisive support of the model with the highest evidence. How much time do I have? 10 minutes. Okay, thank you. So yeah, so in this table here, we have all the models that we computed. Models from this line and above this line are models with the black hole, and these two models are models without the black hole. And the last column right here is the Bayes factor relative to the fiducial model. So the first line is the fiducial model compared with the fiducial model. So this is a Bayes factor of 0, nothing new right here. But if you compare the fiducial model with the model without the black hole, the one that I showed earlier, we have a Bayes factor. It's hard to see, but believe me, this is a Bayes factor greater than 16, which means that we have a 5 sigma detection or 5 sigma favoring of the data with the black for the model with the black hole over the model without the black hole. So this puts some numbers here, just say that our model really prefers, our data really supports a massive black hole. So coming to the title again, this is our final result. If you assume our fiducial model, our preferred model, we have a 36 billion solar mass black hole at the center of the gravitational, of the Cosmic Horseshoe gravitational lens. And if we assume the standard deviation between all the alternative models for the black hole, we have a systematic uncertainty related to the difference between mass parameterizations of 0.12. And to end this talk, I want to put the Cosmic Horseshoe into a bigger picture and try to give some hints about the co-evolution between the black hole and the host galaxy as a whole. So again, this is the m-sigma relation, the mass of the black hole as a function of the velocity dispersion. This is in log scale. And if you see, the horseshoe is just right here in the very mass end of this relation. It's probably the most massive galaxy in this relation so far, and one of the most massive black holes. And in one of the most massive black holes ever observed so far in this region. And if you look at this zooming part of the plot, where we have these very mass end galaxies, we have just a few objects right here, around 6 or 7. And all these systems seems to be above, more than 1 sigma above the main relation, which seems not to be a coincidence, because, yeah, in this region, all galaxies seems to be deviating from above, is not a random scatter around the main relation. And this could be telling us that these galaxies in this regime could be following a different pathway, a different evolution pathway from the other galaxies in the regime, in the relation. So I just want to give a few possible explanations or a few possible pathways for the evolution of the host and the black hole that could explain this deviation right here. And I forgot to say, this is on the plot, but I forgot, the Cosmic Horseshoe is about 1.5 sigma above the main relation. There are other galaxies more extreme, like Home 15A, which is around 2 or 3, 2 sigma. The Abel 1202 is almost 3 sigma. So yeah, a few scenarios that could explain this thing. One scenario is a supermassive black hole binary merger that could be happened in the earlier stages of the galaxy evolution. In this case, because of the dynamics of the black hole merging in the center of the galaxy, this will expel stars from the central part of the potential, which will change the velocity dispersion. But the black hole, the final black hole mass will remain largely unchanged, which means that we'll be observing very massive black holes, but with a lower velocity dispersion than we expect from the normal relation right here. Another possibility is that the AGN. Another possibility is that the AGN could be released. This black hole could be AGNs in the past when they are accreting material. And because of the AGN activity, they release energy from the surrounding material and stop the star formation in that area, which again could be decoupling the evolution of the host as a whole with the evolution of the black hole, of the growth of the black hole. And there's a third possibility that's being in debate and becoming very popular nowadays, is that these supermassive black holes or ultramassive black holes right here, they could be remnants of luminous quasars in the early universe, which means that these massive black holes are already very massive in the earliest stages of the universe, And through the evolution of the time, they only grow more and more in mass, and this don't necessarily follow the same evolution of the host galaxy. So just a few scenarios. It's hard to say which one is more likely or which one you prefer, because as I said, we only have a few objects in this region. Well, because of the time, I'll be skipping some other astrophysical implications. But if you want to know more, I have like 3 or 4 slides about this. And I want to let you with my take-home messages, which is, well, we detect the presence of ultramassive black hole with a 36 billion solar masses at the center of the Cosmic Horseshoe. We did this for a galaxy far from the local universe. The horseshoe is at redshift 0.44. Which typically we don't have this kind of constraints because it's really hard to measure black holes outside the local universe. And we were only able to do that because we had the combination between stellar dynamics and gravitational lensing. If we look at the Bayesian model comparison, our measurement is very robust against variations of the mass profile. And our measurement points that the horseshoe is above 1.5 sigma, above the M-sigma relation, which seems to be common between other very massive galaxies. And this could be an evidence or an indicative that this very mass end of the M-sigma relation could be following a different evolutionary process. One thing that it's nice to say is that there are a lot of future surveys like Euclid, the LSST, CSST, and many others that will be observing almost the entire sky. And with that, we hope to find much more lenses. And some of these lenses will be radial arcs. And with the radial arcs, as I showed in the presentation, and I hope I showed this well, we can constrain the black hole mass in a broader redshift range and with a high confidence. So in the future, we hope that our sample of these very massive black holes will increase, and we'll be able to make a more consistent and robust model to explain why these black holes seems to be deviating from our local scaling relations. So I think that's it. Thank you so much for this. And if you want to see more of my work, you can check my webpage right here, and also come talk with me. So thank you.
Any questions?
This slide is where you present the data for models. Yeah. It's right. You say delta log larger than 5 is size, but it's size against it. Because the 0 is the best, it is 16 point.
No, this is the relative evidence, the relative space factor relative to the fiducial model.
Yeah, but why do you put the size?
Because if you have a difference between two Bayesian evidences, which is the base factor, and if this is
against the model, that's it.
Yeah, against the model with the lower Bayesian evidence. Yeah. Yeah.
Yeah. When you put the
Hi, Carlos. Can you ask the people to go closer to the microphone?
Yeah, if you could talk closer to the microphone.
go back to the slide, right?
Which one?
And can repeat the question.
Yeah.
Okay, there, no, the other one.
This.
That.
Yeah.
You put there residual
Yes.
with respect of what
Yeah.
are the limits.
This is
What?
this is the residual after we subtract the lens light right here. This is the image we observe. So
You said that's the image,
the image, yeah.
and you produce the residual subtracting something, a model.
Yeah, we perform a modeling of the lens light distribution. We are using a multi-Gaussian expansion parameterization. It's just a way to parameterize the light distribution. And we remove the lens light, subtracting the model from the lens light. So this is the residual.
I didn't understand which model.
Which model? The model of the lens light. I'm not sure if I'm being clear. No, I didn't talk about that right here because there's a lot of information. But yeah, one of the things we did right here was to perform a light modeling to one, subtract the lens light and be able to observe the radial arc. And we also use the lens light model that we made of the lens galaxy to constrain the stellar mass, because we have one stellar mass light ratio that just will converting the stellar light profile that we built right here to build our stellar.
So, about the galaxy.
Yeah.
The big galaxy.
This is another feature of it. So yeah, this one
It's an elliptical galaxy.
is elliptical. Yeah.
And probably for the models, you have used a luminosity profile.
Yeah.
Which luminosity profile?
Yeah,
have
it's
you adopted?
not a luminosity profile, it's a parameterization. It calls multi-Gaussian expansion. I think I have one slide about this. I think I have one backup slide for this. So here, right here. We parameterize the stellar light profile by a sum of two-dimensional Gaussians. Each Gaussian has its own luminosity, peak luminosity, and its own axis ratio. So this is the how we parameterize the light distribution. It's not a Sersic or exponential profile. Yeah. No. It has this formula here because this is more generic, I guess, and we are able to reproduce other features that a one Sersic profile is not able to do. For instance, we are able to capture.
When you use the real profile, like the
I think that because this profile in some sense is more robust, because we can capture deviations from a Sersic profile. A Sersic will have just one ellipticity, for instance, and in this model we can have one ellipticity for Gaussian components. And if you look right here, the ellipticity is changing. In black is observation, and in red is the model. We can capture deviations. So in principle, this is more robust than using just one Sersic. And there's a second I forgot the word. Second reason to use this kind of parameterization, because we can use the same light profile in the dynamical model. Is how the code is written. So there's two reasons. One is that this profile is very robust, and we can describe different components of the galaxy with just one profile. We don't need to put like two Sersics with two different index or something like that. And the same profile goes into the dynamical model straightforward. So it's very simple to implement as well.
Another question is when you, the slide where is it dynamic?
be this one.
I didn't understood well. The dynamic is from the images from the spectrum. You assume a model.
We have to assume a model, yes, but we are constraining this model using the velocity and velocity dispersion that we measure from the spectra. So the observations come from spectra. I think I can use this. So this is observations. This is the velocity field. And this is the equations that we assume as a model. Yeah. And provided some mass distribution.
Your model is a disk.
Oh, yeah, this is just one picture. This is just a picture to represent, but actually we can use the same equations to describe the stellar motion of elliptical or disk galaxies. There are some assumptions behind it that we need to be careful. Like we are not able to reproduce galaxies in interaction, for instance. But in principle, the Jeans equations are quite general, and we can reproduce both disks and ellipticals without much issue. But this equation here, this two, is describing the second moment, which is a tracer for the velocity dispersion. There's another set of equations describing the velocity field. It's different from that. And if you want to model a disk galaxy, you probably want to use those equations because the velocity field is the dominant part. And sometimes you can neglect the dispersion. In the elliptical case, or in this galaxy at least, the velocity field is not dominant. The velocity dispersion is dominant. So we can neglect the velocity part and model just the velocity dispersion. So here are just the equations for the velocity dispersion part, because this is what we are interested in reproducing.
I think we have a couple of questions online. Anna, then Thaisa.
Hi, this is Thais. I'm with Anna. She raised the hand for me. Hi, everybody. I just want to ask the key observation that, revealed this such a high mass black hole. I wonder if the gravitational lensing modeling could constrain somehow, or it's mostly, as far as I understood, it's mostly the velocity dispersion profile that constrains the fact that you have such a massive black hole.
All right, so let me tackle this question in two separate ways. This paper here is by James Nightingale and collaborators, 2023. This is the second time a supermassive black hole was detected using only gravitational lenses. This is a simulation from the paper, but they used the data from the ABO 1202 galaxy, where they have a radial arc, and using just gravitational lenses, lensing, because the galaxy was closer and the signal to noise of the radial arc was much greater than the one I was dealing with, they were able to constrain the black hole using just gravitational lenses. And this is what we expect to do with Euclid and CSST, because they are imaging surveys. So we expect to see more radial arcs and be able to detect more black holes.
But
using
can you show me in this picture, which is how I see, what is telling me this two, without black hole and with black hole? What's the difference? I cannot see from the pictures.
Hope you can see my hand here. Not sure. On the right, we have one additional flux. Yeah, thank you. Right here.
Yeah.
Without the black hole. If you look on the image on the left, we are not seeing this extra.
So this means that there is a black hole there?
This means that you have a black hole there.
Because you don't have any light, is that what you're saying?
Because you don't have enough flux and you change the shape of the radial arc. It's a combination of both.
Oh, the shape of the radial arc is different. So the presence of this radial arc reveals or not the black hole there.
Could reveal, yeah. It's a way to constrain the black hole mass. If you don't have the black hole, the radial arc, your lens model will not be so sensible. I would say will not be sensible at all about the presence of the black hole.
And the mass is constrained by this method or not?
The mass is constrained. Yeah.
Okay.
Actually,
and the other, you confirmed with that there is this increase in dispersion.
Yeah, so about my work with the horseshoe, we need to combine both informations from lensing and dynamics, because our radial arc, if you look at this image right here, is very faint, and the signal to noise is not so great. So,
and what is the little dot to the left there? Oh, it's...
Sorry?
There is a little dot to the left.
Yes.
In the residuals. Yeah. What
So
is that?
for our work, you see the dots right here or here?
I mean, even in the residual zoom, you see to the left something. Yeah.
This we try to address this thing, but we believe this is a poor subtraction of the lens light because of the center. This is just in the center of the galaxy, so there's a lot of contamination. It's really hard to subtract the very inner subpixel, I would say, mass distribution.
So the residual zoom here, the zoom, these things that are residual are not saying anything about the black hole?
The residual right here.
Yeah, to the,
The residual here.
These residuals say anything about the black hole or no?
Residuals are constraining or helping to constrain the black hole mass.
Okay.
This is the thing that we want to reproduce, and we are only able to reproduce this, including the black hole mass.
Okay, thank you.
Do you have more questions online?
I have one more. Can I ask?
Yes.
So thanks for the talk, Carlos. Very nice. I was wondering if you have any gut feeling of what are the processes that will give the birth of such, or the preferred processes that would bring about such a supermassive, ubermassive black hole, and if it's related to the environment, because you show some galaxies that are quite well known, and they seem to be in very, very dense environments, in coma, and or being, these ones. So can you talk a little bit about that?
It's not very clear so far, because these galaxies, we have different environments right here. Like the horseshoe, we believe it is a fossil group. So one possible explanation is that every other galaxies and everything coalesce, I don't know the verb in English, but has a coalesceu in the center of the potential, and this could explain, this could point to some binary black hole merger, for instance. But one of those galaxies here, I don't remember exactly which one of them, but it's one of the three. It's actually a field galaxy. We don't have anything around it at all. I think that is NEGC 1600. It's a field galaxy. Yeah, and we don't have any clues about any other galaxies around it or things like that.
But it could be a compact group also, this one.
Yeah, it's hard to say. And the other galaxies are mostly BCGs, brighter clustered galaxies, like Holmes and the Abel 1201. So it's not very clear so far because we have just a few data points in this region. But one thing that seems to be common between all of them is that they are elliptical and very massive galaxies. This the only thing that I can think right now that they are have in common is being elliptical, so very old, and very, very massive as well.
Thank you.
We are running out of time, so you can send an email to him, and we can talk during the coffee break. Okay. Okay. So let's thank him again. Have some coffee and cake. Feel free, help yourselves.
Tchau, pessoal.
Tchau.